The topic of the day is thin film interference. Thin film interference, as the name gives away, is an interference thing that happens. You'll recognize it from the colorful reflections you see in soap bubbles. Or if you've ever been like at a gas station on a rainy day and you look at a puddle and there's shimmery rainbowy effects on the top of a puddle, that's also thin film interference. To get to understanding the interference, we're going to have to take a little bit of a backtrack to remind ourselves of some things we learned before. The first backtrack is all the way back to grade 10 optics when you learned about something called refraction and the index of refraction. We know, especially after grade 11 waves and sound, that the speed of a wave depends on the medium. We now know that light is a wave, so whenever light goes from one medium into another, since it's changing mediums, it's going to change speed. What you focused on in grade 10 is that if the light enters the new material on an angle, then the light's going to bend. We call that refraction. Index of refraction is a number. We short form it with the letter n, and it tells you how much slower light is going in that new material compared to how fast it was going in air. So for air, we say the index of refraction is 1, and for every other material, since light slows down in those other materials, for other materials the index is going to be greater than 1. Like if we had a material whose index of refraction was exactly 2, that means that the speed of light in that material with an index of 2 is half as fast as what it was in air or vacuum. Here's kind of where you spent your time in grade 10 optics. Let's say we have light going from a fast medium to a slow medium, that means the light is going to bend towards the normal. So in grade 10 you would have talked about how we've got these light waves or light beam marching towards material, and when it gets to the material, when I taught it I would say like this edge of the light wave hits the material first, so it slows down first, so that pulls the whole wave. So now instead of traveling this way, it's now traveling this way. So it's whatever angle it hit at, it's now refracted out at a smaller angle. That's where you spent a lot of time in grade 10 optics. What I need for grade 12 physics is we need to push it a little bit more. Yes, the light is going to bend and change direction, but also we know that every wave follows the universal wave equation, V equals F lambda. In grade 11, we said that since we were never changing mediums, we always talked about how the speed of the wave was constant. Now we're changing it. In grade 12 wave optics, the speed of the wave isn't constant anymore. The speed of the wave, if we go from air into something, the speed of the wave is going to decrease. So if we've got this equation, V equals F lambda, if the left side of the the left side of the equation decreases, then something on the right side of the equation has to decrease as well. The way it works out in nature, and it might seem counterintuitive, but the frequency of the vibration doesn't actually change. Frequency stays the same. So as the velocity or the speed of the wave, as the speed decreases, then what changes on the other side is the wavelength. So a second part of refraction we didn't cover in grade 10 optics. We didn't talk about the wave nature of light, but now that we know that light is a wave, whenever the speed of the light changes, the wavelength is going to change also. So this is great. This graphic up here is actually pretty good. In the one medium, you can see the lines are rather spread out. That's showing you the one wavelength. And the one wavelength here in the fast medium is larger. And then when the light gets into this new material where the wave was slower, you can see that the wavelength has literally shrunk down. Another graphic I found online, if this out here is air, and then this here is some other transparent material like glass, let's say. When light enters the glass, not only does it slow down, we don't need that for grade 12, but what's more important for grade 12 is that its wavelength shrinks. So now look, its wavelength is like this big when the wavelength used to be, this big. So the wavelength has shrunk as well. The index of refraction, that n number you learned in grade 10, not only does it tell you how many times slower, but it also tells you how many times shorter the wavelength becomes. So if we had light in air and it hits a material with an index of refraction of 2, the speed is going to be half as fast and the wavelength will be half as long. So quick little equation, the wavelength in the new material, I'm going to use the little prime or the dash for that. The wavelength prime, the new wavelength, is the old wavelength, the wavelength that had an error, divided by the index of refraction. When we do thin films, it's about light entering a film, and then the effect, how we get interference from light being in the film. So we're going to have to use this equation, this lambda prime equals lambda over n, to figure out the wavelengths in those new films. That's enough for this little video, and then we'll keep going with the second thing you need to remember.